In this problem, A is the matrix whose rows are 1, 0, 0, 2, 4, -3, and 3, 2, -1. Part A says give all eigenvalues of A. Part B says for each distinct eigenvalue lambda, give the dimension of the lambda eigenspace, in other words, the geometric multiplicity. And part C says is A diagonalizable? Answer yes or no and explain briefly. Do not find matrices PD, etc. So PD are the matrices that are involved in the diagonalization of A. So the question just asks, is the matrix diagonalizable or not, and explain why, and it doesn't ask you to actually come up with the diagonalization. All right, so take a few moments and work on this problem, and then we'll go over the answer. Okay, let's go over the answer. So give the eigenvalues of A. Well, I have a 3 by 3 matrix, so to find the eigenvalues of A, we just do what we do, which is to find the characteristic polynomial and then find the roots. So first I'm going to do A minus lambda I, and then that's just going to be the matrix you get by taking away lambda on the diagonal. And let's make sure we leave plenty of space to do this. And then we calculate the determinant of this matrix. So I have a 3 by 3 matrix, and when you calculate the determinant of this, I'll do it here, you get 1 minus lambda times the determinant of the 2 by 2 matrix from the cofactor expansion. So that's going to give me 4 minus lambda times -1 minus lambda minus 2 times -3. Now I have to expand all this out. Oh, and then when I continue the cofactor expansion, since I have zeros here and here, the cofactor expansion will just give me 0 when I calculate the determinant. So I just need to expand this out. So I'm going to get 1 minus lambda times -4 minus 4 lambda plus lambda is -3 lambda, and then plus lambda squared, and then plus 6. Is that right? Yeah, I think that's right. So it's 1 minus lambda times lambda squared minus 3 lambda plus 2. And now, remember what I'm trying to do is I'm trying to solve for lambda when I set the determinant equal to 0. So I actually want to factor this as completely as I can. And right now I have a factor of 1 minus lambda. So let's factor lambda squared minus 3 lambda plus 2. Well, that factors as lambda minus 1 times lambda minus 2, right? So I set this equal to 0 because I'm trying to find the eigenvalues, and I'm solving for lambda, and we can see that the roots are going to be lambda equals 1 and 2. So the eigenvalues of A are 1 and 2. Part B says, for each distinct eigenvalue lambda, give the dimension of the lambda eigenspace. So I have two distinct eigenvalues, 1 and 2. So for lambda equals 1, what do I have to do to calculate the dimension of the lambda eigenspace? The lambda eigenspace is the same as the null space of A minus lambda I. So I'm trying to find the dimension of the null space of A minus lambda I. So A minus lambda I, that's A minus 1 times I, is, okay, I subtract 1 on the diagonal, so I get 0, 0, 0, 2, 3, -3, 2, 3, 2, -2. Right? Let's just double check. Yeah. Now can I see what the rank of this matrix is? This is a 3 by 3 matrix. The rank of A minus I is 2, right? So by the rank nullity theorem, the nullity is 1. Because it's the number of columns, 3 minus the rank, which is 2. So 3 minus 2 is 1. Nullity of A minus I is 3 minus 2, which is 1. Then for lambda equals 2, I have A minus 2I, and that is going to be, so I have 1 minus 2, 4 minus 2, and negative 1 minus 2 on the diagonal, and then everything else is the same. Now what is the rank of this matrix? Well, I see that, okay, one way to do it is to do the elimination. I guess I'll just do it out. So you do row 2 goes to row 2 plus 2 times row 1. So I get this and then this. Yeah. And now I can see that when I do the elimination again, I see that row 2 and row 3 are the same, so I'm going to get 0, 0, 0 for the bottom row. So what's the rank of this matrix? It's 2, right? So the nullity is 1. So the dimension of the lambda eigenspace for each lambda is 1 and 1. Part C says, is A diagonalizable? Answer yes or no and explain briefly. Well, in order for A to be diagonalizable, the algebraic multiplicity has to match the geometric multiplicity. So in this case, the geometric multiplicities are 1 and 1, but if you look back at the characteristic polynomial, here, the multiplicity, the algebraic multiplicity of 1 is 2 because I have a 1 minus lambda squared, right? And I have the number 1 is the double root of this polynomial. And then the algebraic multiplicity of 2 is 1. So, but the important thing is that the algebraic multiplicity of 1 is 2, not 1. And in order for the matrix to be diagonalizable, the algebraic and geometric multiplicities have to match. So the answer is no, because the algebraic multiplicity of 1 is, which is 2, is not equal to the geometric multiplicity of 1, which is 1. And that's the answer.